Colloquium speaker, Professor Li Yanmin from Sichuan University. The title is on the screen.
First, I'd like to thank the organizer for invitation. Today, I talk about the extreme metric on toric manifold and the affine technique. Suppose net omega be a convex domain. We consider the following equation. This equation is a fourth order equation where L is some given function and U is a smooth and strictly convex function defined in this domain. And big Uij denotes the cofactor matrix of the highest metric of this one. And A equal constant. So you can see this is fourth order PDE. This PDE appears in different geometry problem. For example, when A equal to minus n plus 1 over n plus 2, then and L equal to 0, then the PDE is the equation of affine maximal hypersurface. And when A equal to minus 1, the PDE is the Abreu equation. So we would like to discuss these two equations, Abreu equation and the affine maximal hypersurface equation. First of all, I talk about the affine maximal hypersurface. Let M be smooth manifold of dimension n and xm to r plus n plus 1 be hypersurface given by a smooth strictly convex function, this function, defined on the convex domain. Because f is strictly convex, then sum Fij dxi dxj is a Riemannian metric. We call this metric the Calabi metric. Sometimes we also consider another metric. Let rho, we introduce a notation. Rho is determine Fij with some power. Now this is a metric. This metric is called the Blaschke metric. We denote Y equal to delta Bx over n, where x is potential vector field, and delta B is the Laplace with respect to the Blaschke metric. The vector Y is called the equi-affine normal vector field. Y has the following property. First of all, Y is transversal to xm. Another one is if we take a differential, the dy belongs to the tangent plane. These two properties is very similar to the Euclidean unit normal vector field. So this is called the affine normal vector field. Because these properties, we can write partial y partial xi equal to some Bij partial x partial xj, where Bij is a matrix. We denote by lambda 1 up to lambda n the eigenvalue of this matrix. And let L1 equal to sum lambda I over n. Then in affine difference geometry, people proved that lambda 1 up to lambda n are affine invariant, is called the affine principal curvature, and L1 is called the affine mean curvature. So affine maximal surface, M is called the affine maximal surface. If L1 equal to 0 everywhere, the PDE for the affine maximal surface is this PDE. Which is the Euler-Lagrange equation for the following variation problem, where delta I is a volume element of the Blaschke metric. There are two famous conjecture on the complete affine maximal hypersurface. One is called Chen conjecture. Chen is Professor Sheng Chen, very famous geometer. Suppose fx1, x2 be a smooth strictly convex function defined on a whole R2. Suppose M is a affine maximal surface, then F is a quadratic polynomial. This is a conjecture by S.S. Chen. Another conjecture is Calabi conjecture. Suppose Xm to R3 be a smooth affine maximal surface. If M is complete with respect to the Blaski metric, then M is quadratic. These two conjectures, the difference is that on the completeness in Chen conjecture, the completeness we call the Euclidean completeness. This means the graph in Euclidean without a Euclidean boundary. This is completeness with respect to the Blaski metric. This because we usually assume Xm to this is locally convex immersion, so with not global convex. So usually the completeness with the Blaski metric and the Euclidean completeness difference, not the same. These two conjectures are generalized to high dimension. For two-dimension case, both conjectures now have been solved. First of all, Chen conjecture is by Wang Xujia and Tu Dinger. Another Calabi conjecture is by Li and Jia. For higher dimensions, the two conjectures are open, so we don't know how to do. For a graph, we would like to use Calabi metric. In this case, we introduce the following affine invariant. First of all is this one, nabla rho, the norm square over rho square. And this one, this also affine invariant. This usually called the peak invariant. And we put theta equal to j plus phi. Li and Jia proved the following differential inequality, which is important in our papers on the extreme metric on the toric manifold. Suppose F satisfies this Pde. This is called the scalar curvature in extreme metric case. Then we have the following differential inequality, delta phi greater than this one. This inequality is very important. Its application above differential inequality, Li and Jia prove the following Bernstein property. Let omega belong is a domain, and F be a smooth strictly convex function. Suppose that this is complete with respect to the Calabi metric and satisfy this equation, means the scalar curvature equal to 0 and the Calabi metric is complete, then for n less than 5 the graph must be at any paraboloid, means F is the quadratic polynomial. In the following, we want to talk about the extreme metric on the toric manifold. In this case, the Pde is called the Abreu equation. Let m omega 0 be a compact Keil manifold. For any Keil metric, define a functional where S is the scalar curvature. The metric is called the extreme if it is a critical point of this functional. The Euler-Lagrange equation of this variation problem is that the gradient of the scalar curvature is holomorphic vector field. For example, if S equal to constant, then omega is extreme kind metric. About this problem, usually there are three aspects of the problem. One is the necessary condition for existence. Another is sufficient conditions of existence. Three is uniqueness. The necessary conditions for the existence are conjectured to related to some stability. There are many works, many papers about this aspect. The famous conjecture is called Yao, Chen, and Donaldson conjecture. Let M be a compact, complex manifold, and L be a positive line bundle. The manifold M admits a constant scalar curvature in the class if and only if ML is K-stable. The uniqueness problem has been solved by Mabuchi in the algebra case and by Chen, Tian, Chen, Li, Hao, Bellman, and Delzant in general case. On the other hand, there has been not much progress on the existence problem. The reason is that the equation is highly nonlinear and of fourth order. So this problem is very difficult. It may become simple if the manifold study admit more symmetry. Donaldson initiated a program to study the extreme metric on toric manifold and solved the problem of the constant scalar curvature for the toric surface. So following Donaldson, we studied the existence problem on the toric variety, toric manifold. We talk about the Abreu quotient. Given a toric manifold, we denote by M0 the open dense subset of M defined by this one. So the point belongs to M0 if Tn action is free at this point. There are two types local coordinate on toric manifold. One is complex log affine coordinate, so Wi, defined by this way. Another coordinate is called the symplectic coordinate, cos I, yi. We can describe M0 in complex log affine coordinate. In this coordinate, M0 can be written in this way. Rn times I Tn means the set x plus Iy, x belongs to Rn, y belongs to Tn. In this coordinate, the Tn action is also very simple by this way. The Keller form in this coordinate is given by a potential function f, which depends only on the x coordinate, independent of y. So we write f equal to fx, and f is a smooth, strictly convex function. It's a convex function. The gradient of f defined as a map called the Roma map, we denote by delta f, whose imaging is now to be convex polytope, and cos I is partial f partial xi. The function defined in this way is called the Delzant transformation of f. We write u equal to LF. Conversely, we also f equal to LU. The moment map restricted to this coordinate is given by this one, projected to x1, xn, and by the Delzant transformation, the normal map to this one. This is a moment map. In symplectic coordinate, M0 can be described in this way, and the Tn action is given by this one. In terms of the coordinate xy, the ridge curvature and the scalar curvature can be given respectively by this formula, Rij equal to this one, and R equal to this one, this formula. In terms of the coordinate cosine and the Delzant transformation function U, the scalar curvature can be written in this way, where Uij is the cofactor matrix of the highest matrix Uij, and W equal to the inverse of the determinant. This is usually called the Abreu equation. Guillemot construct a natural Tn invariant Kähler form denoted by omega g, and let V equal to Lg, where G is the potential function of the Guillemot matrix on the log-Kähler affine coordinate. Suppose that delta is given by linear inequality, the delta Delzant polytope, and where mu I is a primitive inward pointing normal vector to the first Fi. Then we write Li is a linear function, and the V can be write the sum Ai times log Ai. This is a smooth and convex function. This is a symplectic potential function of Guillemot matrix. The problem prescribed scalar curvature problem reduced to find a smooth convex solution in delta for this Pde. This is Abreu equation, where k is a given function, and subjecting to the boundary condition u minus v belong to C infinity delta bar. So the problem, this geometry problem, reduced to solve this Pde problem. This is a Pde, but the boundary conditions are very special. This is Abreu equation. Following, we talk about so-called the K stability and the existence of extreme metric for any smooth function K. Donaldson defines a functional in this way, where Lk is a linear function. Linear. This is a linear function. Fk is now to be the Mabuchi functional, and Lk is closely relative to the Futaki invariant. The Euler-Lagrange equation for Fk is this equation. Is this equation. Donaldson proved that if V satisfies the above equation, then V is absolute minimizer for Fk. This is an important property. We give a definition for some called K polystable. Suppose K is a smooth function. Delta K is called the relative K polystable if LKU greater than 0 for all piecewise linear convex function U, and LKU equal to 0 if and only if U is a linear function. This is called a relative K polystable. Sometimes, for simply, we call the polystable. Donaldson also introduced a stronger force of the stability, which we call the uniform stability. We fix a point P, an interior point of delta, and say U is normalized at P. If U, for any point cosine, U cosine greater than UP and UP equal to 0, then we call U is normalized at the point P. Definition. Delta K is called uniform stable if there is some constant lambda greater than 0, such that LKU greater than lambda times the integral u over partial delta. Sometimes we say delta is k lambda stable. So, Gabo also had proposed a notion of uniform stability for general kind of manifold, and its version on the toric variety can be read in this way. Here, this some norm such as this one. One can easily say that the uniform stability implies the polystability, but the inverse is unknown. But in general, we know. But in the dimension 2, it is proved by Donaldson that when n equal to 2, if delta k is polystable and k greater than 0, then there exists a constant lambda greater than 0 such that this is k lambda stable, so uniform stable. In this case, k greater than 0 and n equal to 2. Wang, Xujia, and Zhou show that this relative k stability implies the uniform k stability when k is a affine linear function. For general case, we don't know that. This is also for 2 dimensions. But for any dimension, we can prove the following result. If the Abreu equation has a smooth solution in this space, then delta k is uniform stable. This space means for any u belong to this space, then u minus v belong to the C infinity delta bar. So we proved that, this means we proved that the uniform k stability is a necessary condition for exist a smooth solution.
For any k?
For any k, yeah, and any dimension. For any dimension, we also get a result so-called the interior regularity. This result is this one. Let delta be a Delzant polytope. If delta k is uniform stable, then for any solution u of the Abreu equation and any omega 1 belong to delta 0, and any constant alpha between 0 and 1, we have the following estimate. So uck plus 3 alpha less than some constant, and this is the norm of k, ck norm, where the constant c is positive constant depending only on n, the dimension, and k, alpha and omega, and lambda is a uniform k stability. The depend on omega and lambda in the uniform stability. So from this result, we know in the interior of the of delta, the solution is smooth. But on the boundary is a very different case. So far, we don't know how to do. And the important step, key step in the proof is we get the following estimate delta uij in terms of f. Then we use the estimate for linearized among the Abreu equation due to Caffarelli and Gutiérrez, and estimate for Mons Abreu equation due to Caffarelli. Then we can go to the interior estimate. Now we want to talk about the main result is about extreme metric on toric surface. On toric surface, the first result is by Donaldson. He proved that when M is a compact toric surface, if it is it meets a constant scalar covariance metric if and only if delta is k-polystable. This is proved by Donaldson several years ago. Now we talk about our main result. Our result is for 2 dimensions, only for 2 dimensions. Let M be compact toric surface, and delta be its Delzant polytope. Let K be an edge non-vanish function. If Mk is uniform stable, then there is a smooth T2 invariant matrix on M that solves the Abreu equation, where edge non-vanish means the given function K is not identical 0 on any edge. Right? On every edge, K is not identically 0. In this case, we can prove this result. So, given this function have solution if and only if this is uniform stable. Extreme metric, it is well known that CP2 blob 2 point could not admit any KE metric, but one can construct extreme metric. Can be constructed extreme metric on CP2 blob 1 point by use ODE method, and Chen, Brown, Weber constructed the extreme metric on this surface. For any dimension, it is known that omega f gave an extreme metric if and only if R is a linear function of cosine. Let A be a linear function of cosine. Because LA U equal to 0, if and only if U is a linear function, then this is a set of n plus 1 linear constraint on A. So there is a unique linear function A satisfy above constraint. For n equal to 2, all above theorem, including the case of extreme metric case. So we can use this. We talk about the method to prove this result. The proof is we use the continuity method. Let K be a scalar curvature, and suppose there is some constant lambda such that delta is K lambda stable. Now we take the unit interval I. If t equal to 0, we start with null metric, for example, the Keil metric or the Greenman metric. Then let x0 be its scalar curvature. The delta must be k0 and lambda 0 stable for some constant lambda 0 greater than 0. This is from our first result, first theorem above. At t equal to 0, equal to 1, we set k1 lambda 1 equal to k lambda. And we set kt in this way and lambda t in this way. Then it is easy to prove that kt lambda t delta is kt lambda t stable. So in the following, we let L be any edge and cosine L is an interior point such that k at this point not equal to 0. Then there is some disk such that this one belongs to this one, and k, absolute k greater than delta, where d is defined by this way. The picture like this. We can show if we modify the metric G, we can show that in the whole path, the kt satisfy greater than delta in the disk in a disk. So in the following, we note big lambda is a set T such that this PDE has solution in this space. So we should show that lambda is open and closed. Openness is standard. People can see the paper of Donaldson and Abreu. It is remain to get estimate for solution to show that the closedness. This is important. Donaldson have proved that in interior regularity for 2 dimensions and get the C0 estimate. So we need to do more estimate for example, for the behavior near the boundary and estimate on the boundary of the polytope. This case is mostly difficult case because the boundary of polytope corresponding to the interior of the complex manifold. So if we choose the complex coordinate, then we reduce to derive an interior estimate. But in this case, we should extend our real affine technique to the complex case. The affine technique, the Abreu equation is very similar to the maximal equation in affine geometry. So the affine technique, including the differential inequality, the Bernstein property, and the affine blow-up analysis, play important role. Then, for example, we have now estimate for delta phi. Then we can use this estimate and blow-up analysis to get the following estimate. There is some constant C independent of U such that the following hold where theta p times d square, this is some constant, where du means the geodesic distance from P to the boundary. So from this estimate, we can now the behavior near the boundary and derive the interior estimate also.
What is
Theta in before is phi plus j. Oh, moment. Now. Yeah, here is the definition. J is this peak invariant, is short order differential, and phi is this one. To do affine blow-up, we make the following affine transformation, like this one. T star R. This is by a matrix, a constant matrix. Here is lambda constant. Where A is a affine transformation on this space, we may write a hot. Let U be a function T star, then this transformation induces a affine transformation on U. U star equal to lambda U, in this way. So by calculating directly, we can prove that after this transformation, the determined transformation rule is like this one. And the metric and the theta and the scalar curvature, also the rich curvature. Yeah. So because we take the affine blow-up because the advantage is that the affine blow-up changes the geometric quantity can be easily calculated. So we can calculate this one under control. For complex manifold, in complex coordinate, we can prove a similar differential inequality is delta phi. Let omega be a domain belong to Cn. Denote this space is a real function satisfy Fij bar less than 0. Then we denote W is determine Fij bar, and the psi is this one. The log W, the Laplace log W, and the square norm. We define P equal to this one, where kappa and alpha is constant. Then suppose F satisfy this equation. Here is a scalar curvature. In toric case, this is a given one. Then we denote by square is a Laplace operator. Then we have the following Pde, difference equality. This equality is very important for us. This equality play key role in our paper. We use this inequality and use affine block analysis. We can go to the estimate for rich curvature in a geodesic ball like this one. This is how for any z belong to the geodesic ball with a radius a over 2, where C1 is a constant independent of F. Because we got the estimate for rich curvature denoted by H is determine Gij bar over Fij bar. Gij, G is the potential function of the Guilherme metric. We want to estimate this one. We use the above estimate on rich curvature. We can get the estimate for H such that H is bounded above and bounded below by constant. Then we can get other estimate. Finally, we can prove the closeness. So in this case, we can prove our theorem. I want to stop here.
Any questions?
Then we can go back to Rich estimate.
Rich estimate, yeah. You want to see it? This one. The rich curvature we can estimate in terms of this one. W is determined, and also the maximum of W is the geodesic ball. But use this estimate, we can go to estimate of H. Then we can go to the W.
So this is the
immediate step. Yes. Immediate step.
So in the boundary of the ball, the W.
Yeah.
We need this one, the maximum of W.
I see.
But from this one, finally we can go to estimate for H. Then get estimate for W. Then finally we go to this one, rich curvature.
So you get this by maximum principle?
Yeah, maximum principle. Estimate this block analysis, then go to our estimate for psi to derive the contradiction.
I see.
It is difficult to use maximum principle to estimate this one, because if we take the Laplace is very difficult, very complex. We cannot estimate this one. So we use block analysis. We use this estimate for psi. So psi is very important for us.
Psi is it?
Psi estimate. No, here we this estimate for psi.
Psi like the first direction of the determinant.
I don't write here. Yeah. And today, Bohui Chen have talked about this one. Yeah. The most important that is this differential equality. The estimate for psi use this equality on the geodesic ball. So this is very important.
I see. But you know the behavior of P in the boundary of the geodesic ball?
What? On the geodesic?
In geodesic ball, do you know the behavior of P in the boundary?
This is depend on the complex, on the complex manifold. It's an interior estimate.
I see. Oh, okay. So you're smooth.
Yeah, smooth. On a geodesic ball. It's for the geodesic ball. In the second paper, we can prove on any edge, any different point, their distance. There's bounded below by geodesic. So we can use this one.
At the beginning of the talk, you mentioned a larger family of equations with alpha. The question is whether these techniques can also be used for other equations in this family.
Yeah, for the family of equation, I have a result for 2 dimensions, but if A between some constant, I forget the number, then it must be polynomial. Correcting polynomial. This result generalized to the result of the Chen conjecture, and also got the result for Abreu equation. And yesterday, Stony have proved on the section. So we got a more general result, but only for 2 dimensions. For higher dimensions, so far we also don't know how to do.
So you have the Bernstein theorem.
Yeah, Bernstein theorem for this one.
5.
This for this condition is color B matrix is complete. We can go to the n less than 5. If in the Euclidean complete, we only 2 dimensions we know. For higher dimensions, so far we don't know.
Any other questions? Okay, let's thank Professor Lee again.
Thank you very much. Thank you.